So as we begin to work our way into engineering, I want to start with what I call the big picture, a big glossy view of what we're doing with engineering. And then in later videos, we'll start talking about the nitty-gritty details. But I think it's important to kind of keep in our mind what the big picture is behind what we're trying to do and how we work with earthquakes. Most of these videos deal with building design, bridges, uh, dams, all types of infrastructure, have different methods of addressing earthquake events. Some of the points from the bridge or from the building design are also relevant to bridges and dams, but of course, those are very different types of structures. They have their own characteristics of how they respond to an earthquake. So I want to talk about what I'll call the big picture. So we get an idea of where some of the future topics are going to fit into place. What really happens during an earthquake is moving the ground, it's shaking the ground back and forth and the foundation of the structure. And so what's really happening is inertia wants to hold the main structure in its original position, but the foundation literally gets pushed to one side. Now that causes bending of the columns, beams, walls, whatever, which then pull the main structure horizontally and begin to accelerate that in a horizontal direction. Primarily, the issue we deal with is the horizontal motion of the structure. We'll see later a little bit about the vertical effect of the earthquake, but the dominant response that a building has to survive is the horizontal movement of those floors of the building. And it's a very complex, dynamic, multivariable situation. It's a little too complex to be able to work with in a basic engineering approach. So the first thing we generally do is we think of the mass being accelerated as really being an equivalent inertial force. And instead of considering the dynamics of the earthquake motion, we're going to replace that with what I'll call an equivalent static load that we can use in combination with the other loads we need to design buildings for. I generally use the initials EQ, meaning earthquake. I'll try to be consistent through most of the slides that way. Let's look at what might be a three-story building. First off, buildings have to support, of course, their own weight and their live load, but we have to have some kind of a system in the building that resists any horizontal forces on the building. And usually the same system is used for either earthquakes or for wind. But for example, here's a three-story building which uses shear walls as the resistance for horizontal earthquakes from wind or ground. We want to keep in mind that when we count stories, we're interested in how many floors are above the ground. A one-story building is essentially a roof. A two-story building, three-story building, we may have three occupied areas, but the bottom area is actually standing on the ground. What we're interested in is what's supporting the building above the ground. Well, the first thing we generally do is we start to think about this building. We cut the building halfway between each elevated floor. Now, in general, most of the weight of a structure is located in the floor. concrete slab or the wood flooring. So and the walls are relatively light. So we often lump all of the weight from anywhere above that red line into what we assume is a single weight or mass at the story level. Now it's a dynamic event going on, so that mass gets accelerated. But as I say, we usually replace that at mass times acceleration with an equivalent lateral static force that's being applied at each story level for the design of this building. The walls on any particular floor have to resist all of the forces that are being applied to stories above the wall we're interested in. So for example, this upper level, the shear on that third floor shear wall is going to need to be be equal to the horizontal force generated by only the roof. If we go down near the bottom of the building, now the shear on that first floor has to resist all of the forces being applied on all of the stories. We use the term base shear, which is going to be the total lateral force applied to all stories, and generally the shear that has to be resisted by the lowest level of the building. There's a real basic procedure that a lot of building codes and a lot of design work follows. First, we determine the design criteria. For the vast majority of projects, that's going to be the building code. However, sometimes the owner of the structure may have their own design criteria that either equals or exceeds the requirement of the building code. Now we stop to determine the period of vibration of the structure. We determine the seismic coefficient, and then the design force is defined as the seismic coefficient times the weight of the item we're designing. And then the final step, we're verifying that the structural component is strong enough to resist whatever forces we expect it to have applied. So the seismic coefficient of an item is the ratio of the design force to the weight of the item. We will find that there's a seismic coefficient for the building. There's a seismic coefficient for an individual floor. There's a seismic coefficient for the clock that is mounted on the wall. Each time the building code talks about this is the seismic coefficient for an item, keep in mind that means the design force is that seismic coefficient times the weight of the item that is being shaken. Earthquakes shake the base of the structure, which caused the mass of the building to accelerate. It's a complex, three-dimensional dynamic situation. We're going to replace it with what we'll consider an equivalent static force so that it's something that we can work with and have quantifiable values to determine. Seismic coefficient is the ratio of the seismic design force to the weight of the object that's being designed. And base shear is going to be the total lateral force applied to a building during an earthquake. Thank you.